from this house, but nevertheless he's active in different communities, different institutions. Like in particular, the institute he's running, the Institute for Design Science. Originally, he had so his background was in physics, in theoretical physics, and also in mathematics. He has also then right after a background on philosophy, literature, and also has interesting books to read, interesting literature to read, and I have the joy ever since I met him in Barcelona 15 years ago, the joy of having shared so many things, and I am also part of the institute, and he's also part of this Glossal Lab initiative. So originally for about the encyclopedia that I have been talking about before, and Glossarium Vitri, he has been one of the most also important persons in the and also for the development, something that we will discuss later. But he's going to give us now some orientation of some of the things I've been talking before. So it connects also to the problems that Jorge was stated in the beginning. Then when I saw you about the way to see the knowledge system, so he's going to give us some hints about the aspects on semantic coherence in Glossal Lab using Topos theory. So thank you very much, Rainer, and I will be listening.
I'm just looking for the appropriate arrow.
I think
this one.
Yeah, this is to go ahead. To go ahead.
Yeah. Very good. Okay. Yeah. Thank you very much. So I can quote Wallenstein. Late comest thou, but thou comest. Unfortunately, this morning I could not be on time. So what the idea is, I will just give you some impressions shortly, but what I will do is to first, in the first part, give you the general idea of what actually a topos is, because that is not general knowledge. The second point is to show how that is connecting to the topic we have here. And the third is a kind of mini example, very, very simple, but only for indicating what one would actually do in practical terms, not only in the theoretical conceptualization. So the first idea is to generalize the meaning for conceptual networks, such as Glossal Lab is obviously one, in order to model the implications for ontological as well as epistemological aspects of the underlying syntax and semantics. Obviously, as you have already recognized, there is a strong connection to linguistic aspects, and this is why syntax and semantics becomes prominent here. Topos, I'm sorry for my voice, that's due to my grandchildren. Topos theory in the mathematical sense is the adequate instrument for this enterprise, and it can also illuminate the generic connection between geometry and logic on the one hand, and cognition and communication on the other. These are actually the concepts who are, so to speak, meta concepts if you compare them with the inventory of the Glossal Lab network. So I just point out some literature. I'm simply dropping these names and later on some technical concepts in order to give you a hint and a signal for the case that you might be yourself interested in looking much more in detail. So Topos theory starts actually with a very famous work of Artin, Grothendieck, and Verdier, Théorie du topo et cohomologie étale des schémas, that is in Springer lecture notes in mathematics in 1963 and 64. And this actually explains the ambiguity in the pronunciation, because the Americans thought that topo would be a French expression. So the plural is toposis, which is not quite right, because topo is topos in Greek, and the Greek plural is topoi. So there's only one mathematician who has recognized this. That is my colleague Goldblatt from Australia. We have actually been both visiting fellows at the University of Bologna at the same time. And he has written a very impressive book on topoi, the categorical analysis of logic. In fact, you see another detail here. He calls that the categorical analysis coming from mathematical categories. But nowadays, the Americans call that categorical analysis, which is not correct, because categorical has a different meaning, obviously. So you see, even when you are doing mathematics, it is always important to look at the meaning of things. Well, the most central work on topos is Johnston. That is another colleague from Cambridge. He is at St. John's College in Cambridge. I'm at Clare Hall. And he has written 2 volumes. The 3rd volume is announced, but has not yet appeared, unfortunately, called Sketches of an Elephant, a Topos Theory Compendium. And this is relating to that famous Indian fairy tale, you know, where you have these chaps looking for an object in the darkness, and all of them have different results, but in reality it's only an elephant of whom they have some aspects. And this is, of course, meant as a metaphor for topos theory. Well, and MacLean Murdoch, Chiefs in Geometry and Logic, is also very important. And Stanley Vickers, formerly from Imperial College London. I've known him well a long time ago. I met him 25 years ago when he started this work. And he has written a very important book on locales and toposes. So, idea of topoi, possible applications, and many examples. First, I talk about mathematical categories. A category C is a class of objects called objects of C, and a class of morphisms of C, such that each morphism has a unique source and target object respectively. You see, if you compare this with the set theory you know from school, you realize that a set consists of elements only, and these elements are always the same. If you have the set of real numbers, it's always the same set. So it's not changing, actually, it's static. But in nature, things are dynamical and they're changing in time. So this is what the morphisms care about. Yeah? And the best to understand what objects could mean are, for instance, the inhabitants of Munich. You see, you have all objects of the category Munich are the inhabitants, but they are not static at all, because some are just being born, some have died, some migrate to Berlin, for instance, very well known, and some are actually coming into the city. So you have actually four morphisms for the objects, and they are describing the development of the set of objects inside the category. So in other words, a category is practically a dynamical set. So also we have certain rules, and most important is the composition, that is actually the sequential ordering of operations acting on morphisms. So for every three objects ABC, there is a binary operation of the form morph of AB cross morph of BC is mapped to morph of AC, and this is called composition, such that the laws of associativity and left and right identity laws are valid. That is quite straightforward and is something, a guideline for working with that. Now, a topos is very similar to a category, but this is a category with a specialized logic structure. Hence, a category turns out to be a special case of a topos. In fact, the most important point is that usually categories obey Boolean algebras, while a topos has a generalized Heiting algebra for its logic. The difference is mainly in the negation. In the Boolean algebra, the negation of a negation is again the original proposition. But in a Heiting algebra, the negation of a negation is unequal the original proposition. And that is mainly due to the time development in between. Yeah? In particular, a Grothendieck topos. Grothendieck was very famous French mathematician, but of German descent, actually. A Grothendieck topos is a category that admits a geometric embedding in what we call a pre-sheaf category. And mappings between categories are called functors. So in fact, you are generalizing the laws, you know, from functions on sets to functors on categories. And if the category has a special form, then you call it a Grothendieck topos. I would not like to go into much details for explaining everything. So because I'm heading towards the first general example, so we leave that for the time being. By the general theory of geometric morphisms, every Grothendieck topos sits inside a category of such pre-sheaves by a geometric embedding. And this may be taken as an alternative definition of sheaf, and goes back to another mathematician, William Lorvier, namely Lorvier, Tierney topologies are bijectively given by geometric embeddings instead of explicitly defining a sheaf as a pre-sheaf satisfying descent as a special property. So in other words, to think of what a Grothendieck topos might be, you can say, well, a Grothendieck topos is essentially a category where the objects behave like open sets in the usual topology. And this is a very elegant connection between geometry, topology, and analytic mathematics. Okay, I skipped the propositions, and as I said before, I claim that they are proved. But you see here already that there is a difference between local and global, namely in the sense that global refers to the gluing of sheaves, covering of data. The expression covering, especially coming from Grothendieck, and that goes back to the open sets terminology, because if you have a covering, then it means that some object is covered by open sets. Of course, they have an average, we will see that in a minute, but the gluing of sheaves or the covering of data means that each global datum is the coverage of a glued local data. And that is very similar to what happens actually in the network, because you look for alternative interpretations of concepts, but the global concept, so to speak, shows up as a gluing of local concepts. So then there is an alternative definition by Giraud, and then Johnstone is differentiating this somewhat, and also our colleague Street. And I will not go into all these details. But here shows up a very important point, that is what we call the Yoneda embedding. And this is relating to a mathematical property which takes care of the various perspectives you can take with respect to an object. This comes actually from the theory of music, and I will comment on this shortly. So, can skip some of the material. Of course, all these transparencies show you only a stepwise approximation to the general concept of Grothendieck Topos, but we don't need the details here. And I can continue. I can continue directly with a more funny example. It actually goes back to a paper of Newman and Nave, 2008. And I've discussed this example several times already. Namely, those colleagues demonstrate the relevance of mathematical categories and topoi for cognitively generated concept formation. And they give concrete examples from child development. That is very important, because you have to remember that children, what they learn is what they learn for the first time, you see, and therefore you can realize what the underlying epistemological ground for this might be. In fact, their approach is related with respect to the children's development theory by Jean Piaget, which goes back to 1992 and is actually discussing already mathematical aspects, namely topology and geometry. The basic idea now is to represent the concept constructions by means of what in mathematics we call a push out and a pull back. We see that in a minute. Take A and B and C as individual cases of some concept D star, which is represented by the sign or by the name D, playing in turn the role of denotating the respective cases as to their associated name. Then the push out is defined by the following diagram. You see, A, B, C are the single individual cases of D, of what we call D, but the concept is different from the name. This is mainly because we have different languages. Yeah. For instance, if D stands for dog, then the concept D star is universal, but not the name, yeah, because it could be a chien or whatsoever. Yeah. So now we do the following. We take as individual cases sorts of dogs. Yeah. We call C Chihuahua. These are the small dogs, you know, you utilize for cleaning your don't worry. So C is Chihuahua, B is Great Dane, and A is German Shepherd. Now test then A according to whether it can consistently fall as individual case under the name dog. Obviously, the idea is to look for a similarity criterion in the first place. If A can be shown to be sufficiently similar to B and C, then it falls under D and is thus mediated with the concept D star. This looks so, yeah. So you have from German Shepherd, which you're looking at, and that is equivalent to explaining a child what a German Shepherd is as compared to all the other dogs the child might already know. So from the German Shepherd, there is a mapping to Chihuahua, which means it's a similarity mapping. Yeah? The mapping tells you German Shepherd is similar to Chihuahua. And going upstairs, German Shepherd is similar to Great Dane. Similar because they have 4 legs and all that, yeah, and the tail and whatsoever. From the Great Dane, you know already that is falling under the name dog. So this mapping from Great Dane to dog is an identification mapping telling you the Great Dane is a dog. Yeah, so the first mapping is similar to, the second mapping is a. Likewise, Chihuahua is a dog. Yeah. Now, for dog, for the name dog, there is a universal concept which is D star, that is, so to speak, the universal dog as such. And you can argue now, if the German Shepherd is similar to the Chihuahua, and if it is similar to the Great Dane, and if Great Dane is a dog and Chihuahua is a dog, then also German Shepherd is a dog. So that is very similar. It's not complete, but very similar to one half of the modus ponens, which is crucial for computer logic, Boolean logic. Now you have also and then it's becoming more complicated. You have also to think of humans using words in metaphorical terms. So, for instance, the child has learned about dogs, and now someone talks to the child and calling an uncle old dog. Yeah. So the similarity criterion is obviously difficult, but it's still acceptable, you know, if you work with reductions. I mean, this uncle might have 4 legs, but not really, yeah, but I mean, in the transformed sense. And yeah, whether it's an old dog or not is difficult to explain. But what the child learns in metaphorical terms is that for one name, there might be another concept which is similar to the original concept, but it's not exactly the same. And you realize already what we have here is that sometimes we have to work with abductive inference because there is no logical deduction or induction possible. And this is very similar to the relations between concepts, because what you look at is a stability criterion according to which the concept remains in a certain playground, so to speak, where you can modify it. And of course, you have to be able to reverse the errors, because then the push out is called a pullback. And this is because the child has to understand this procedure in both directions. So it goes either from A to the name, that is bottom up, or it goes from the concept to the single case, that is top down. Yeah? Only if the child can do both can we say that the child has understood the concept. And of course, in the case of a human child, it's becoming even more difficult, namely when you replace the name D by D prime, which is called a hot dog. Yeah? Because obviously you have a different concept which belongs to hot dog. And you might remember that the duck sound is sometimes called sausage dog in England. And the background is that what we call hot dog now for having fast food is actually a German invention brought to the US. And the first US people did was to compare this to a duck sound, you see, because of the form. So all owners of duck sounds are not happy about this. But you see what I mean? This is a very wide metaphor, actually, but of course, the child gets accustomed to thinking of this space of replay available with metaphorization of concepts. Okay. Yeah, some shorter papers you can find by John Byers and his colleague Stay, or by Goldblatt again, or Saunders MacLean and Aikem Murdyke, Johnstone in the Elephant Book, and actually also by a paper of myself and Wolfgang Hofkirchner published at a conference on semiosis in Vienna. So finally, a topos is, in this sense, a category with terminal object and pullbacks, with initial object and push-outs, with exponentials and sub-object classifier. Now, we had most of that we had already, because the German Shepherd was once an initial object in the push-out, and it can also be the terminal object, top-down, in the pullback. And similar properties called exponential sub-object classifier, they deal with the kind of objects involved. I will not elaborate further on this. Okay. So this is the general idea, I think. Oh, by the way, I would like to point to a book I've brought all out with the Munich colleague Wiedemann. I think he is still professor at this institution here, and we have published a book on a glass bead game that is an expression coming from Hermann Hesse, from a well-known novel. This is actually the first glass bead game which can be played on a computer in reality. So perhaps you look up the Springer publisher website, and when you come to this book, you have an extra entry for the software involved, and you can try to play this yourself. And as I said, as to the Yoneda lemma, this goes back to a theory of topos applied to music by the Swiss colleague Mazzola, 2002. And the idea was that this Yoneda lemma is capable of integrating different perspectives you can have with respect to the same object, such as a piece of composition, for instance. So, okay, then we have possible applications. Now, one of the objectives of GlossaLab can be formulated as follows: to reduce redundancy in how concepts are used across fields, and to clarify overlapping or confused uses, to expose differing metaphor, theories, and conflicts, to build a more coherent conceptual framework for the concept of information as it appears in various disciplines. I think most of that you have just heard from Jose. So in the GlossaLab framework, the coherence problem concerns whether a network of concepts, relations, and definitions forms a consistent and interpretable whole. It adds whether the conceptual system defines a connection semantically. I wonder whether we had a glass of water.
Oh,
Yeah, probably fine. So, roughly speaking, it asks, given a collection of concepts and their interrelations, does there exist a model or interpretation that satisfies all those relations simultaneously? So we are asking, is the conceptual system internally consistent, and how are meanings unified across contexts?
More.
Is that legible? Roughly. So you can, this problem, you can compare to Topos theory. Namely, you have conceptual systems and a category. You have a concept, object, and a topos. You have relation and morphism or sub-object.